This is a worked example, and I'm going to show you that, in a sense, the repeated measures t-test or the related samples t-test is a one sample t-test. Why? Because we're going to transform two variables into one variable. So, for example, in a one sample t-test, we have a sample with all these numbers. We've got a mean, we have a standard deviation, and then we want to compare this mean versus a pre-specified value of a population. Sometimes this value is 0, most of the times, but sometimes we've got another number that for some reason we want to compare against. And basically what we have to do, calculate the t-score. What's the t-score? We do 65.6 minus that specified value and divide it by the standard deviation, but divided by the square root of n. And the square root of n here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the square root of 10. So what do we do in the related samples t-test or repeated measures t-test? We've got participants contributing to two values. So this 45 and this 24 is the same participant. 60 and 26, same participant. Another participant, but the same contributing to these two scores. Then another participant contributes to 75 and 34, and so on and so forth. So instead of calculating the mean of these scores and the mean of these scores, which we can do, and we provide the descriptive statistics of these values, mean and standard deviation of these two sets of scores, but we obtain the difference between these two scores, and now we use this variable. And we can do exactly the same as we did with the one sample t-test. Okay, so we calculate the mean of these difference scores, and in this case is 31.4, and we calculate the standard deviation, which is 16.23. Then we compare this mean with the pre-specified mean value of the population. In this case, the pre-specified value is 0. So why we compare with the population mean value of 0? Because the null hypothesis in this case is that in the population the mean of different scores is 0. So we are saying that these two conditions that we are comparing, there is no difference in the population. That's the null hypothesis. Okay, so in this case, researcher is interested in the role of presentation format on the understanding of probabilities. And he presented a number of problems involving probabilities in two formats. The probability format that uses percentages, like 52%, or proportions, 0.52, and the frequency format, in which the same information is presented in frequencies, like for example 52 out of 100 instead of 52%. So 60 participants went through both conditions. So then it's a repeated measures design. And then the researcher calculated the percentage of correct problems solved in each participant in each condition. So we got the independent variable, which is presentation format, and we've got two values, probability format and frequency format. And we've got 60 observations in each of these two conditions. Then the dependent variable is problem-solving performance. The null hypothesis is that the difference score in the population of interest is 0, and the alternative hypothesis that the difference score in the population of interest is different than 0. Okay, so mean difference score is the score in probability format minus score in frequency format. So we calculate that for each of the participants, and that gives us a score of minus 20.7. And the standard deviation of these different scores is 13.4. So here we've got a descriptive statistics. So we've got here the group, not the group, is the same group of participants. So this is only one group, but this is when the group goes through frequencies, the performance is higher than when the group goes through the probability format. And the difference is 20.7 points. In order to compare the mean difference scores obtained in our sample with the t-distribution, we need to somehow standardize the mean difference of scores. So the t-score is the mean of different scores divided by some standard deviation. So what's standard deviation? Well, that's the standard deviation of the sampling distribution of different scores. So what's the sampling how do we calculate the standard deviation of the sampling distribution? Well, by having the standard deviation of the different scores in our sample, and then we divide that by the square root of n. Because the standard deviation we have in our sample was 13.4, that's the standard deviation of the different scores, and we divide that by the number of observations, which is 60, and that is altogether 1.73. That's the standard error. And then when we got, when you do the difference, minus 20.7 divided by the standard error, this gives us negative 11.96, which should be significantly different. So we've seen t-distributions, and t-distributions are similar to the normal, but a bit larger tails, fatter tails, but the idea that the symmetry is the same. So we need to obtain the p-value. So what p-value corresponds to this t-test? So in order to determine that, in the olden days we have tables to do that. Now we just ask the software to calculate that for us. So you saw in previous master classes that the t-score is distributed in a way in which the values that are close to the mean, which is 0, are more probable than values that are further away from the mean. So the further away you go from the mean, the lower the probabilities. So if we have an 11.9, that's quite a pretty large t-value. So it is the probability of obtaining that score or more extreme is very, very small in the sampling distribution. So therefore, here we've got a p-value is a very small number. So we here we see the t-distribution again, just to reiterate that a t-distribution with one participant looks like this, but then as soon as you've got 4 participants, then 8, 12, then the t-distribution becomes closer and closer to the normal. Okay, so where is 11.9 or negative 11.9 in this distribution to determine whether that value or more extreme one has some degree of probability? Well, as you can see in all these distributions, 11.9 would be very to the left, so because it's a negative number, so it's very extremely unlikely that this came from a population in which the null hypothesis is true. Therefore, we reject the null hypothesis.